Archana worked in ENSCESS 2010 to 2015. She was in ENSCESS and worked in the Central Geomatics Lab. So it's my great pleasure to welcome back Dr. Archana to the ENSCESS Earth Science Forum. And it's my I'm very happy to introduce Dr. Archana to all of you. She joined in the Department of Civil Engineering in Indian Institute of Technology, Guwahati in 2021. Till that time, and as assistant professor in 2015. And in 2010 to 2015, she worked as scientist in Central Geomatics Lab in ENSCESS. And she did his BSc in Geology from Government College, Nattagam and Kottayam under MG University. And after that, she did his MSc Tech in Applied Geology from Indian School of Mines, Dhanbad. After that, in MTech in GIS and Remote Sensing from IIT Mumbai. And her PhD was on spectroscopy, remote sensing and planetary exploration. And the title of the PhD was Reflectance and Thermal Emission Spectroscopy of Terrestrial Rocks for Spectral Remote Sensing and Image Analysis. She has a number of high impact papers to her credit, and currently she guides 9 PhD students, out of which 2 have already graduated. And her research interest is in remote sensing for planetary exploration, petrophysical modeling, then thermal IR emission and reflectance spectroscopy, hyperspectral remote sensing for mineral exploration, and then remote sensing and GIS tools for hydrogeological studies. So it's my pleasure and honor to welcome Dr. Archana to the Science Forum, and I request her to deliver her talk. Thank you.
Thank you. Thank you, Dr. Thompson. And that was a wonderful introduction for me. Thank you for that. So, okay, I hope my PowerPoint presentation is shared. So let me just get it. So today, and I am happy to be back to the ENSCESS. That's also, so after coming from ENSCESS, I never had an opportunity to visit again, but my students visited. So I'll also soon visit the ENSCESS, change the environment. Okay. So today what I'll be talking about is based on a remote sensing analysis, how much close Earth and Mars in terms of geology or lithology. Okay, so now yeah, from my when I did my PhD, that time onwards, we are trying to work on this planetary remote sensing. That was one of the objective of my study. And later on, when I moved to other areas, like I had a short spell at in the petroleum industry. Then I had a short spell in ENSCESS also. So that time I couldn't do much about, pursue much on this planetary remote sensing ahead. But that was a time when there was, in India, we had a lot of things that was happening in the same time. We had the Chandrayaan mission that was successful. We have data sets that was received. And so as soon as I joined ENSCESS, I could attend some of those workshops also. The other thing, then later on, the Mangalyaan mission also to Mars was also there. So this type of missions from Indian side helped to build a planetary geoscience community in India also. So and then I was also a part of being there from my PhD days. I was also a part of this group. And today what I will try to elaborate on will be our our studies mainly, and then how that is creating a maybe small change to the our understanding of Mars, because already we know that NASA is very far ahead of all of other countries in terms of the research in planetary geoscience. Okay, so before moving to my studies on related to Mars, we will look through the general aspects of Mars. Why Mars is so curious? Always it remained curious to the humans. So the fact is, when we consider all the terrestrial planets, those planets that are like Mercury, Earth, Venus, and Mars, all these are the rocky planets. The most important why we are more um, curious about Mars is because of the fact that many things are very similar to Earth. So it has a atmosphere, though that atmosphere is not very much like Earth, but it still has an atmosphere, which is mostly carbon dioxide, and maybe recent studies shows there is water vapor also. And then if you consider the radius or the size of the Mars, it's much smaller than Earth, and it's far away from Sun also. But the day length, if you see, is very similar to what we have. And but however, the year length and then therefore the seasons also are different. It is also having seasons, and because of the tilt of the axis. So that tilt of axis is also there, and it has two moons. So these all things are very much comparable, not exactly like what we see on Earth, but still it's more comparable to Earth compared to any other planets which we have studied. And when we consider the geological part, so how well differentiated the interior, the structure of the Mars, then obviously we believe that there is a core which is similar to Earth, but the exact structure is still unknown. Okay, so these are the things. With this background, let us move on. And obviously, as I said, Mars was always curious to us. And if we think about any habitable environment that can be there, then we are thinking that could be Mars, the most possible place. And there are now very recently a lot of research is going on to find um, life on Mars, because we believe, based on the research that has been carried out till now, it feels that there could be. It may not be very like in Earth, but some type of microorganisms or something must be there. That is what people are trying to do. Uh, Obviously, that part is something away from what we do. But before Mangalyaan, so the mission to Mars, if you see, obviously, as I said, we have when there was Soviet Union, obviously there was a race between US and Soviet Union. And here I show pictures of the missions to Mars in a form that the one that reached the Mars orbit, which are successful in terms of, and then there are so many that are not successful. The mission failed. So that you can see. The other thing is the mission success rate for different countries. So if you see that, obviously the race was between Soviet Union, or right now Russia and US, and you can see there was less number of missions from the Soviet side, and then the success rate was only 5%. But in the case of India, we see that that was some great achievement that we made, that our first mission itself got successful. And the success rate of US is obviously high. Other countries that are, you know, already there in this race is obviously the European Space Agency. Then the Japan, China, all have its own place in the Mars mission. And the reason is because of the same fact that we believe that there may be, at some point, we will have some news about life definite evidence of life on Mars, or maybe the next habitable environment that you can build, maybe it's on Mars. So on that, because of these reasons, the missions are there. The Artemis mission has a plan for Mars also. So all those things, when we talk about, I would like to highlight a few missions, which are the missions that are maybe of this decade, especially, because that is what we will highlight on for our studies mainly. So if you see, there was so many landers have been there on the Mars. And when we have landers, then the beautiful thing is that those landers can have instruments, and that is like it can touch on the Mars surface and then get a feel on the rock types that are there. Basically, whenever we go for any mission, the main target to Mars, then the main target will be, one is atmosphere, the other one is on the geology of the Mars. Okay, so when we relate that, then only we can think about habitable environments. And the presence of water is obviously one such big thing that will help us to define whether it will be habitable or not. So for all those reasons, we need lithological. Uh, so sorry for that. We need some lithological or geological evidences. So here we have few missions like Mars Reconnaissance Orbiter. This was in 2005, a successful mission. And there are few data sets that are the remote sensing data sets that came from this mission is still, relevant, and we are using it a lot in Martian studies. A few to talk about is context camera, which is a high resolution images of Mars are you can observe using this context camera. The other one is CRISM. I'll be talking about CRISM datasets in my our own studies. We are using CRISM datasets. And then the next one is that happened in 2011, which is Mars Science Laboratory. And this is where all of us know about the Curiosity lander, and that is a part of this. And Curiosity is still doing its work in Mars for so many years. Before this Curiosity, there was two rovers from the Spirit and Opportunity. And I'm glad that I could have an opportunity to collaborate with those who were the PAs of this Spirit and Opportunity. So those two landers or rovers, were like using the thermal region of the electromagnetic wavelength region. So we will talk about the thermal infrared region and what are the strength of those later in this discussion. So that's Curiosity. The Curiosity is giving, it's a Mars Science Laboratory, and it is equipped with very high-end instruments. So advanced analysis, like a person going and collecting sample and doing the analysis, that type of analysis is done by Curiosity. So a lot of informations are coming from that instrument particularly. And then we have our own Mongolian mission. And then there is another lander that happened to be measuring the Mars quakes. And this was in 2018. And then it also observed a very important quake on Mars due to meteoritic impact. So that also, those analyses are also coming out in the later stages of 2022. And then we have the Perseverance rover. This is the most the highlighting point. So because but we have not analyzed anything from these rovers as such. such. Well, what my studies will be mostly based on the CRISM context camera and the thermal images that we have got. The one reason is because we have different uh, a focus of study or area of study is different. Well, when you talk about curiosity or perseverance rover, these are rovers which are placed in certain locations. And so if we are curious about those landing sites, then only, I mean, there is a point in working on that. So this is that more or less what are happening in terms of mission. And I have also highlighted the most important one for us. Now, when we talk about any research study, then there should be a motivation behind that. So personally, my motivation comes from the fact that when you look around the digital elevation of Mars, then you can see a very striking phenomenon that is called the dichotomy. And this crustal dichotomy is observed in Mars. So you can see here that there is if you see the northern hemisphere and the southern hemisphere of Mars, then the northern hemisphere are mostly lowland areas or having less elevation compared to the southern hemisphere. So, and this is, there is a striking similarity which we can compare with Earth, though it is, we will not, I mean, though it is not that comparable, still there is something striking that will always come across to us. Like when you see, when we talk about Earth, this is a bathymetry of, ocean flow. So you can see that there is this, in case of Earth, it is the reverse, we can say, that we have the northern hemisphere, which is mostly land area or elevated region, and we have the southern part, which is mostly ocean or with a low elevation. Now, I'm not saying that we can compare the process or anything, but still there is this type of a similarity that comes across our mind. Now, obviously, there is no water filled on. So this is comparable to basins. So when we talk about ocean basins and all, this is comparable with that kind of thing. But obviously, water is not flowing on it. And as you know, we don't know where from all this water came to Earth as well. So I will stop that type of discussion there itself. And what I am focusing on for today's discussion, this particular region on the Mars, this is a very dominant feature in the Mars, a striking feature, which is called the Tharsis volcanic province, where you have three volcanic mountains that is aligned in a particular direction. And then these are some of the one of the most biggest type of volcanoes that we can see. And there is another one here also that is called the Olympus Mons. So these are the Tharsis volcanoes, Tharsis Mons that is referred to, and then we have the Olympus Mons. Now the fact that these are aligned in one particular, it shows an alignment, and then we have the other part is your valley region that is also very predominantly, you can see the valley part. So and then there is this strikingly, a very low elevated region. This is called the Hellas, the basin regions. So these are, so mainly my focus will be on these particular so we can always go back and see the Hawaiian island volcanisms, where you can see a chain of volcanoes in a particular, similar to this kind of an alignment. So that is why this particular region is of greater interest to geologists. And So before going further, now this is something that so already I've shown this DEM kind of it is called the molar shaded relief, where you can see the elevation changes in terms of color, and then we have the geology of Mars. It's already documented. Now there will be a difference between when we see the geology of Earth and because here we do have great more detailed information in Earth about the the lithology and the age, because we can do absolute age determination. However, when we talk about Mars, the age is determined using a different technique. So we will go through that also. However, this is the global. So the entire Mars has been documented in terms of the variation in terms of the what is observed on the surface of the Mars, and this is largely predominantly was carried out using remote sensing data sets. Okay, so I was talking about the Tarsis region, and so these are mostly Amazonian aged. So here comes the age that we use. We have classified the Martian history in terms of or time scale in terms of three different divisions. So the youngest one is obviously the Amazonian unit. Okay. So here is the time scale of Mars. And as I said, we don't have any absolute age determination mechanism, or we don't have any fossils. So normally this age is based on the craters on the Mars. So we count the craters and we determine the age. So that is how this is. So we predominantly, there are three different periods, which are called Noachian, Hesperian, and Amazonian. So I talked about the curiosity. So if you see the more information that comes from the Mars, so we have the Amazonian. It can be considered to be the longest, because from 3.1 till present, it is all Amazonian. So it is 3.1 billion years. So from the beginning, so we believe that it all started together. So as on Earth, we start from 4.6 billion years. Similarly, we start from 4.6 billion years, the time point. And then it is Noachian, and then we have Hesperian. Now here we would like to talk about from the data sets that we have received, based on the analysis that has been carried out. It was found that most of your minerals that are that are considered to be OH minerals or water hydrated minerals are coming from this early time period of Mars. And there are no such detection of hydrated minerals in the Amazonian period. However, in our studies, we have shown that there are, we could detect some of the hydrated minerals that I will show from the Amazonian region. But this is what that is, the existing concept. So somewhere before Amazonian itself, water must have flown on the Mars. So these are certain discussions that are happening with respect to whether water was there or not, or aqueous environments were there or not. So such kind of studies, but it is predominantly found to be much older than the Amazonian time. That is what the informations are all talking about. Now, I told you about the various types of rovers or landers that are on Mars, and I told you that we have not worked on a particular lander as such, because of the fact that these landers are positioned in different points only. And our particular interest was on these Tarsis moons, and that's the reason we didn't use any of these lander data sets. So just for so Viking, that was the oldest. It also was a lander. So it landed on Mars in 76. That was the oldest lander we can talk about. And this is a picture from Viking. And then now we have Curiosity rover. It is climbing up the hill and then taking photographs. And then you have the photographs from the Curiosity rover. And then Perseverance also will be, I mean, more data sets are going to come because it just started its mission. And then we have our own, so this is a picture that comes from the Mangalyaan data sets, okay? Now, we talked about the stratigraphy or the time scale that we have for Mars. However, when we have this Curiosity rover, the rover could climb up the hill and it could do some kind of all type of chemical analysis on the surface of the rock that it has been, taking traverse through. And it has, created a very detailed stratigraphy based on that analysis. So these type of detailed analysis are also being carried out. But then, as I said, that these are rovers, so every points on the Mars may not be able to be detected using this method. However, we are getting more and more clarity on what kind of lithology or surfaces that we can have on Mars. Okay, so from there itself, it is very clear that we do have sedimentary rocks or sort of sedimentary rocks on Mars. We do have differentiated, like when we talk about moon, mostly we talk about basalts and anorthosites. And beyond that, we are not talking too much. So here we are seeing that sorry for this, I just locked my door. So here, that is the most important part, that here there are so many differentiated rocks that we are observing on Mars. Okay. So now coming to our studies, I already told that we were more curious about these Tarsis moons, and there were a lot of studies that was carried out in terms of, because when we talk about this particular, type of volcanic mountains that are aligned in a particular direction, obviously a lot of curiosity is going on, because that happens only when you have something like plume volcanism, because that is what we observe as analog on Earth. And that will, if that is going to happen, then obviously that will talk about, because plume volcanism, we need plate tectonics. So then, so those are the things that are that will come to when we talk about these kind of features. And it's not only about this alignment. There are other type of observations that are coming all throughout the Mars, that it has some tectonic features as well. So when we study this, so this was a study that we used, but predominantly we wanted to use our Mangalyaan data sets for this study. And what we did is basically try to see the morphological part. So that is one thing that we use for remote sensing data sets. So when we talk about the remote sensing data sets, one thing is you can study about the surface features. And then the other part of it is coming from the spectroscopy, or based on the absorptions of light absorption patterns or the spectral response patterns, how much we can identify the materials. So one is the surface feature that we observe based on the texture of the image from the images that we have. And based on that, we can interpret. And that is how we interpret the morphological features. And the other part is obviously the spectral responses. And here we have used both kind of analysis in this particular study area. And what we observed is, so as I said, already a lot of research has been already carried out in these modes. And but with our predominant, why we use this is predominantly how much we can use from our Mongolian data set. That was our primary objective of using this study area in morphological analysis. So what we did, we used this, so there is this elevation DEM kind of map, which we call as MOLA, and that observations are used for studying the surface morphology. So we could do a contour, could generate a contour map from this MOLA DEM. And here you can see the this is for the Olympus mounts. So I told about the Tharsis, 3 Tharsis mounts aligned, and there is another one called the Olympus mounts. That is the super volcanic mountain that we have on so in the solar system. It is considered to be one of the biggest one in the solar system itself. And this is how we have observed. And you could see the slope analysis also. Similarly, the profile lines also were carried out, and this is from the Mars color camera image from our own Mongolian data sets. Okay, now, and so the resolution or the clarity of the MCC image was less compared to other data sets like the convex camera, which I talked about. However, it's a pride moment for us to use our own data sets. So this is what we did the analysis to see how the morphological patterns are changing for different mounts or different mountains, volcanic mountains. And then we did a sort of hypsometric analysis. Now here, when we talk about hypsometric analysis, we are normally use it for, Earth landform evolution studies. And here what we try to see is how different are these mounts with respect to each other in terms of this hypsometry. Now it talks about whether, there is any, when we talk about hypsometric curves in Earth, then you can see whether it is tectonically dominating landform or erosionally dominated landform. Now the same criteria we applied here. Now we know that, as I said, we have a clear indication that tectonics is there in place, at least for this Tharsis region, because otherwise we will not have this type of a volcanic mountains aligned in a particular fashion. So from that, again, we are trying to see whether these 3 mountains are showing any difference in terms of its elevation characteristics. So this is elevation with respect to cumulative area, how the pattern is changing. And when we see that, we observe that the Olympus mounts, which is aligned to northern towards the north of this Tharsis, 3 Tharsis mounts, is found to be showing erosional dominance. Now, what type of erosional dominance we are talking about? It could be type of like landslides kind of things. Okay, this volcanic, these are all volcanic landforms. So there are possibilities of smaller kind of landslides or erosional scarps have been identified in Olympus mounts. And therefore, that kind of erosion is what we are talking here. However, if you see this hypsometric curve, you can see that Arcia, that is one of the three chain volcanoes, one of that volcano is distinguishedly showing, very clearly showing some different characteristics. Now we also see that we also try to check the caldera. So any volcanic mountains will have its own caldera opening. And we have seen that when we try to see all the three, four volcanic mountains, this Olympus Mons has so many different calderas. Now that caldera age also was determined based on the crater counting technique. So I told you that we use crater counting technique to determine the age on Mars surface. The same is used in Moon as well. So based on the crater frequency and how big the craters are, these are craters created by meteoritic impact. So based on that, we are determining the age. There are certain models created, and using that models, we are fitting our crater frequency and size and determine the age. So here you can see the caldera, the top part of the Olympus Mons. There are so many. So this talks about episodic characteristics, that not in it has different episodes of volcanic eruptions. So that is one thing that we have tried. And same thing is happening with Ascarius modes. And I told you that Arcia was looking at very different. We could observe only one caldera in the case of Arcia modes. And even this Pavanese modes also, one caldera was observed. But both Olympus and Ascarius had a different calderas formation. Okay. And when we estimated age, so what we did, I have shown the geological map of the entire Mars as such. Now that is not that detailed, like it's a very general map, and that is what we expect from when we have such a very large area. What we tried here, that we tried to figure out how these three modes are showing in terms of age, using the same age determination technique, using crater counting technique. And then we observe that you can see here that there is the age of these modes is relatively older compared to this one. So that's one observation that we had. And this Olympus Mons is now the age, it will not talk about the when it all started, because we have seen that these mons have few of these mons had episodic volcanic eruptions from the caldera counting that we have done. So that also shows that this may not be the 128 this age that it has been shown here for these Olympus mons. It can be considered to be the youngest episode of volcanic eruption. Let us put it in that way, maybe. Now, it is not absolute. I told that we are having crater counting technique. Obviously, after the surface was formed, then meteoritic impact is happening, and then that craters are developed. That's how we are counting it and then determining. So obviously, the error estimate will be much more compared to what we have on Earth. However, it's better to have something than so, but it can be compared relatively. We can say that okay, there is this one was a younger one, and we have also carried out some literature study which also suggests a similar kind of age determination. However, the absolute age will be which we have, and then the other studies have will vary, because we use context camera. Okay, So convex camera, as I said, it is a high resolution image that we have. And within a one caldera itself, in that a small area here itself, you will get CTX images, so many CTX images. So based on that type of analysis we have done. So we believe that more accurate type of analysis we have carried out using high resolution images. So that is one thing that we did. So here the observation is that obviously, like our Hawaiian Island, I'm referring to Hawaiian Island volcanism is because of the, it is still active, and we know that this volcanic, the age of those island chains have been also determined. So we know that relatively it shows a relatively older or younger age patterns in that alignment of islands, volcanic islands. So that is why I am referring to that Hawaiian island volcanism. And then that also suggests that, okay, some kind of similar to plate tectonics on Earth, some kind of activity must have happened for this type of a feature. Well, the next part that we did on the same study area, I told that in the beginning that we have different when we divide the Mars in terms of time scale, the Noachian and Hesperian, that was the time from where the surfaces that are such older surfaces, from those surfaces, there were many evidences of hydrated minerals. Now, how we do this? Obviously, when we talk about Curiosity rover or Spirit or Opportunity rover, these rovers are robotic kind of rovers, and it has its own inbuilt instruments that can do kind of analysis like we do for using X-ray fluorescence or X-ray diffraction method, where we will be able to chemically analyze the rock. Now, other than that, but that is for a point data set. Here we are talking about, we cannot go and do that type of, so Curiosity is covering a very small region during its traverse through that Mount Sharp Gale crater. And similarly, all different rovers have its own locations, and it is moving around that region only. Now, if we wanted to get an idea about other regions, chemistry or mineralogy, obviously I talked about the spectral response. So that is what is this remote sensing is based on. And when we talk about that spectral response, here you can see this the figures, the graphs of several minerals I have shown here. Now, these are all, so this is USGS spectral library, which means these are lab generated spectra of different minerals in the visible near infrared region. In the that is the region we use for mostly for remote sensing purposes. So what we are doing here, we are trying to find out the absorption patterns when light is interacting with the material, then what absorptions it is showing based on the wavelength region. So that is how we are observing this. Now you can see there are several different kinds of minerals are there, and different minerals are showing different absorption features. And when it comes to rock being a mixture of minerals, obviously it is not going to be the same kind of feature that you will observe. But if those rocks are having abundance of such minerals, obviously the absorption feature will be picked out. These are laboratory generated. Now, when it comes to remote sensing data set, obviously we have hyperspectral data sets where you have so many bands of data, and each band is actually talking about a particular wavelength points here. So what it observes, basically we are getting more point data sets from your image. So if you take one particular point in an image of a hyperspectral image, and that particular location can have several points showing the features. So those are the spectral features. Now I hope most of us are now have a knowledge about hyperspectral remote sensing, but still here why I am showing this is to understand the variations in the spectral response of different minerals, and based on that mineral mixtures, then we will get different absorption features. Now our task will be to identify those absorption features and assign the minerals that are showing those absorption features. So in the case of Martian images, the atmosphere is not unlike the Earth's atmosphere. We when we take images on in Earth, we have to deal with vegetation, we have to deal with the atmosphere. Obviously, Mars has a atmosphere which is more of carbon dioxide, but if we have that atmospheric correction carried out, then the other problem like vegetation, all those issues are not there. So in that way, it is better to study Mars. But the challenge is, the other challenge is like, okay, we have only observations based on the data sets that we have. Okay, we don't have the actual sample to look at. Anyway, so I told you about the MRO, Mass Reconnaissance Orbiter, from where we are having the data sets of the convex camera, which I have already talked about. And then the other one is the CRISM. CRISM is imaging spectrometer. So it images. So here I am talking about one point, how it will show the variation with respect to wavelength. Similarly, you will have n number of such points for a particular study, a particular area. So that is why it is called as imaging spectrometer. And the region, wavelength region that it covers is from 0.36 micron to 3.92. And that region is the, you will call it as visible near infrared region. And that is the region where, so we know that colors are because of from the visible region. So if we have so many colors from this, that means that colors are because of the visible wavelength region. And then we have the near infrared region. Now, when it comes to the mineralogy, or why we have such absorption features from different minerals in those regions, it's because of the several factors account for that. One is on the due to the absorptions that happens at the electronic level. Like for example, if you see an iron hematite, for example, or magnetite, iron usually show very vibrant red, orange colors. And that is because of the fact that this iron Fe2 plus or Fe3 plus, in its electronic state, there is some excitation of electrons that happens between in the atom of iron. And because of that, you have colors like red or orange color. Coming to other minerals, like say, for example, if we take a pyroxene mineral, the absorptions that that is happening for a pyroxene mineral called diopside, you can see it shows a very, so this is reflectance, okay? The x-axis, y-axis is showing reflectance, which means a low reflectance always talks about an absorption. This is how we talk about. And it is absorption that matters to us, because absorption is because of the molecules or the atoms that are present in that material. Okay, so here we see a 1 micrometer absorption, and that is very peculiar for pyroxenes. We get a around 1000 nanometer or 1 micrometer, and absorption feature is observed. And this is because of the pyroxene is it has a chain silicate structure, and then it has the silica tetrahedra. We'll have several, there is an octahedral sites for this also. From there will be the transitions of electrons. And that is why we observe such type of absorptions. And these are very strong absorptions that we can observe. There are other absorptions that happens in the near infrared region. Okay, so which is around beyond 2 micrometer, for example. Those are actually because of the vibrations of the bond in the molecules. So there are different reasons. Atomic absorptions are there. There are molecular vibration. So that is called, that particular area is vibrational spectroscopy, we call, where we talk about different types of. So we have SiO bonds. So Si, silicon oxygen bond, that is what we will be concerned about, because we are talking about rock forming minerals. And silicon oxygen bond, it has a bending and stretching vibrations. So each of these, along with the other atoms present, will create vibrations. And that vibration will create absorption features on your in the spectra. Those are called, and those are there are fundamental vibrations because of the fundamental molecular vibration, and there are overtones to it. And what we observe in minerals in this region is mostly based on such kind of, not the fundamental vibrations. Fundamental vibrations are seen in the thermal infrared region. For silicate minerals, I am talking. Obviously, other minerals will have different kind of fundamental vibrations. But here I am talking about silicate, rock forming silicate minerals, which will have its own fundamental vibrations happening in the 8 to 12 micrometer region. And here we see many absorptions that are happening. These are called overtone vibrations because of the OH in the molecule, OH. So that is why whenever you go for a planetary mission, remote sensing studies, you always try to have the spectral region in the remote sensing data sets from visible to near infrared, because there you can observe the overtone vibrations due to OH in the molecules, and that will help you to find out hydrated minerals. So that is the whole thing about the science behind this. And now coming back to our study, we carried out such carried out such analysis to find out whether there is any hydrated mineral presence in the Tharsis region. So we used some data sets. As I said, these are very huge data set. You need in gigabytes you will have for a very small area, because these are hyperspectral data sets. And the same, so we need a lot of, if we wanted to map the entire region, then you need to have so many data sets. And here what we did for the each bonds, we took as many data sets at the caldera as well as on the flanks of this each bonds, and then carried out the analysis. And what we find out was, yes, there are hydrated mineral presence, but the absorption features of these hydrated minerals are slightly obscure compared to what you see here on other areas of Mars where you have identified hydrated minerals. And we have carried out an analysis called mixing analysis, where we have come across that with decreasing a percentage of hydrated minerals, then obviously the absorption features are going to be reduced. However, that will show up in your data set, and you can say that yes, there is this fundamentally the hydrated mineral presence are there along with other minerals. So it is like a combination of minerals are there, due to which this is getting obscured, because it is not coming from. So why this study is important? Because this we are talking about data sets that are taken at a height, okay, and obviously noise will be there. So we need to understand whether it is any features are coming from because of the noise, because it's, as I said, when you have very small percentage of those hydrated minerals, the data absorption will be very small. This has to be cleared out from the noise that you have, the background noise that always we will have. So you can look here. These are from the this lower spectra that you can see. These spectra are from the actual images, and it is compared to the different minerals at the top. The top part is different minerals that we are observing from either lab or clear image data. However, you can see that this shows very good indication that hydrated minerals are present in. So these are also from different modes we have studied, and we showed that hydrated minerals are present on Tharsis modes. And this is something that was new, because as I said, Tharsis modes are the relatively younger one, Amazonian age, and the entire in the entire Mars, Amazonian aged surfaces have not reported any hydrated minerals so far. Okay, so that is the importance of our study. But then what is the reason for these hydrated minerals? Obviously, because these are volcanic landforms, we cannot rule out hydrothermal activity. But if not hydrothermal activity, then it should be an ongoing weathering process. So that is what we have studied from this part. The next one is something that I have carried out in collaboration with Dr. Thompson. So this has not yet been communicated, but I thought this is also something that will be very important, because all through when we talk about planetary geology, the main focus are always on basalts and mafic kind of lithology. And there were certain evidences from, especially from the thermal infrared region in Mars, about granites or granitoids, which are more quartz-rich kind of rocks, or felsic kind of rocks. So such evidences do suggest that obviously Mars may have a different. Obviously, the evidences that are coming from Mars suggest that it's more differentiated. More differentiated rocks will be there. But then we just thought about the possibility of having pyroxene bearing granite, or you call it as tarnogates. So why this is important in terms of planetary studies, in terms of remote sensing studies, this is a special challenge, because I told about the fundamental vibrations and overtone vibrations and the electronic absorption features in the electromagnetic wavelength region, where I told you that just now I told about the stretching and bending silicate vibrations happens in the thermal infrared region, or the fundamental vibrations happens in the thermal infrared region. And then you are observing in the visible near infrared, either it will be a hydrated mineral, or you can have iron in your mineral, like pyroxenes, or magnesium in your mineral. So then only you will get some absorption features in your visible near infrared region. So what will happen? Only when there are pyroxenes or amphiboles or phyllosilicates, we get absorption features. But if it is a granite, for example, without any such kind of iron or anything, then obviously the plagioclase or the feldspars and the quartz may not show any absorption feature in the visible near infrared region. However, the thermal region, where the fundamental vibrations are captured, there we are able to detect quartz and even feldspar. Other features are also can be observed. So that's why in this particular study, we will not be able to use only the CRISM data sets. So what we did, because CRISM data sets are mostly invisible near infrared region, we need thermal infrared. So for that, we used a combination. So we used thermal remote sensing or thermal spectral responses, or along with the reflectance spectral responses. So this thermal region, why we call it as thermal region, is because of that the heat or the temperature of a body will create some emission. These emission patterns are being studied. That's why it's called thermal emissivity. And this particular 8 to 12 micrometer region um, is where you can observe those. So we will see, unlike in the reflectance studies, these are more called as emission studies. Okay, so that is the main difference. Other than that, the data sets that we use, as I said, is the MISS data sets. Uh, so that is for the Hallas basin. What we observed is we use CRISM data sets as well. So for the same locations, what we observed, so this is what I was talking about. Like when you have, you need both visible near infrared region. So this is the characteristics of granite and pyroxenite. So this is very, now it will be very clear that when we have granite, it is because of OH, OH will be showing, okay? So OH features may be captured, albeit, or this is not a absorption. These type of absorption features are basically due to OH in your mineral. Okay, maybe because of weathering or any such kinds can result in this type of absorption. So this is not considered to be a very fundamental type of absorption feature, unlike what you see. So here you can see this is the pyroxenite sample, this is the granite sample which we have from the field, and this is how the different minerals that can be related to granite sample shows the absorption. And similarly, the pyroxenate sample. So here you can see clearly the absorption feature that is coming around 1 micrometer, which I have already told you. Now let us look at the thermal region. Okay. So in the thermal region, the granite shows, see, this type of quartz. The quartz feature is picked in the granite. And obviously, the other features of albite or microcline, and a combination of, obviously it will be a mixture, so there will be a combination. And these mineral spectra are from USGS spectral library. So that is one thing that we have. No, this is from this is the thermal spectra. This is from Arizona State University Spectral Library, ASU Spectral Library. And for the visible region, it is from the USGS. We ourselves also are trying to build, but we don't have that many, pure minerals are required. Characterization is required. So we are building our own, but it is not as good as what USGS or ASU is having. And then you have pyroxenate. So this is how the thermal region and the visible region looks for. Now we have Charnakite rock. There are 3 different Charnakite rocks that we have, and those rocks are showing different kind of spectral features. This is in the visible region. And similarly, we have in the thermal region as well. The same Charnakite rocks in the thermal region. So as I said, you are seeing the quartz the quartz feature in one of the sample. Very clearly you are seeing the quartz feature. And similarly, you can see now based on the presence of those minerals or the mix, it is a mixture that we are receiving for the rock. So there will be a variation in the absorption feature as well. So that we can model, and from there you can also find out the thermal. One thing about good thing about thermal region is that in thermal region the spectra are linearly mixing, and so the linear mixing models are much mathematically more simple compared to non-linear mixing models. So in the case of visible near IR, we have to use non-linear mixing models. Okay, so the highlight of this our study is that you see the lower part of this graph is showing HB1, HB2. These are from the Hellas Basin. Okay, now here you will see that these features are showing a slightly different from what you have observed in the thermal region that you have seen in the past slide, the last slide. So, but this is because this is from the Themis data set. The Themis band number is much less. It is not like hyperspectral, like CRISM data set. So here you are seeing the CRISM data set, okay? And here you are seeing the Themis data sets. Now, how based on the Themis dataset and CRISM dataset from the same locations, we are observing the coexistence of quartz and mafic minerals, which could possibly point out presence of rocks that are similar to your Charnock. So this has not been published, but this is what we are trying to find out. And that's all from my side. I would like to thank all of you, and thank Dr. Thompson and Dr. Strilash for giving this opportunity.
Thank you, Dr. Archana, for the wonderful talk. If there are any questions, you may please ask.
Hello, ma'am. I'm Padma Rao.
Hello.
Yeah, first of all, thank you very much for a wonderful and interesting talk. I'm just I'm a seismologist. I'm just wonder, you are talking about the volcanoes on Mars. So
Yes.
Is there any evidences of seismicity in nearby regions?
So seismicity, I talked about that InSight lander, no? InSight lander. InSight lander is observing seismicity in Mars. Okay, so what they have observed there, one particular observation which they have made is because of one meteoritic impact. It has been recorded around 4 in Richter scale. So that is evident. But what they are trying to figure out, is there any, I mean, other than meteoritic impact, any other like what we have as earthquakes, whether we have mass quakes. So that is still under observation. It's a very recent development. Okay, so it is getting, but we have several indications of tectonic activities in and around those regions.
Okay. Thank you, ma'am.
Yes. Extensional features are very prominent in my Tharsis region, no, which I have studied. We have extensional tectonic features that are very evident in those regions.
Okay. Thank you.
Archana, one question is that based on your hyperspectral data, so in the Tharsis region,
yes.
Have you identified any lithology? Like, could you do any lithologic mapping from that region?
So as I said, we use this CRISM data sets. Okay, so it is very very small area can be observed in one single image of CRISM. So what we did, we took several such CRISM images and then tried to map the lithology based on the same basic principle that I have explained in using absorption features. Then what we can do is those regions where we have the data sets, there we can identify because we always get a mixture spectra. We will not be able to say, okay, this mineral is present or that mineral. We can talk about that this type of, it is a mafic type of a lithology or predominantly mafic type or predominantly felsic type or predominantly maybe you can say pyroxenite kind of mineral, rock type that we can observe. Or so right now what we did is whether we are observing any hydrated minerals. Okay, so there we can say, okay, it is mafic, this is altered mafic. Like that, we are trying to differentiate.
But one question I have, it's a general question. As I understand, this Martian surface is covered with soil.
Dust. You are talking
Dust,
about
yes.
dust.
Dust, yes.
Yes.
So, and there are storms there, dust storms are there.
Yes, yes.
So, is it really, how really we can pinpoint, based on the hyperspectral, this sediment is derived from particular region, like can we say?
So yeah, so that was even when we did our that paper on hydrated minerals, the same there was this question which we have to address. So what we did is in that for that particular like how to model dust or how to know whether dust is there or not, we can use this again thermal region, thermal infrared region. Because I myself have studied that with the grain size change, this thermal region can pick that change because predominantly in the thermal infrared region, the light scattering, okay, what we capture is more of surface scattering.
Okay.
So what will happen when the these are getting powdered, then the volume scattering predominate. So based on that, what we did is we could identify whether there is a dust component in those regions where we are studying from the CRISM datasets, or it is less. So for that, we did an initial screening of our region using the thermal infrared datasets.
Okay.
So that is important. You are correct. That is important before making any such statements.
Okay. Thank you.
This is Jyoti. Hello, Archana.
Hello, sir. How are you?
I'm good. Have we met any time?
Yes, when you visited Guwahati, I was the coordinator.
Oh,
of that.
yeah. You were the convener that time. Yes. See, this Thompson's question is probably, I will rephrase it. What he is basically saying that if you have dust and you are relying on remote sensing, you will get only dust composition. So how do you know about the rock beneath it? That is what he is asking. But I think what I have heard from people like you, they believe that in that one region, dust actually do not migrate too far. So the average composition of the dust will be similar to what you have beneath it. They don't migrate like thousands of kilometers.
Yes, that is one thing. But still, for our observation, what we because we were talking about hydrated mineral presence, so
Yeah.
we need to rule out that the dust component is relatively less in those regions. So for that, we relied on thermal infrared analysis.
So I have a question regarding this volcanic activity. If I understand, all these activities stopped by 3.1, or is there anything in Amazonian also? Any volcanic?
It stopped maybe around 1.2.
Okay. So the question is this. I mean, we know Mars probably doesn't have plate tectonics like Earth. Then how you explain this volcanic activity, or how does melting happen in Earth's mantle?
So that's the question. So I believe there is tectonics having a role. That's what our studies are also showing.
Some kind of tectonics is there.
Some kind of tectonics are there, playing a role in.
All right. Thank you for a nice talk. There is a question by Unni in the chat box. Thompson, you can read it. He has something there.
Okay. Yeah. So, a question by Dr. Unni. What he's telling is that yes, it's a layman's question. I'll read out. It's a layman's question. One, Earth's size, that's radius approximately 6,371 kilometers, is much larger than Mars. The highest mountain peak on Earth is 8.8 kilometer approximately. However, on Mars, the highest mountain peak, Olympus Mons, is around 22 kilometer. So what's the scientific reason? Second, do Mars volcano cause lightning? If yes, is it possible to analyze lightning spectra using remote sensing CCDs and use them for studying details of volcanism / magma / mineral contents, etc. on Mars?
Second question, I may not be able to comment on. But the first question, what I believe, I mean, whatever with the knowledge I have, what I believe is like we have active tectonics as well as we have active weathering and erosion on Earth. So
on
if
Mars.
We have
yeah.
on Earth, which is not there on Mars, that it explains why Olympus Mons is still at 22 kilometers. So if you don't have upliftment happening, and if only erosion is happening, then there will not be elevated regions, correct? And if there is no erosion happening, then the elevated region is going to remain as such, correct? Whatever elevation it is achieving. And then there is another thing also. It's all, it's not only, this is what I can explain, like if there was a 22 kilometer elevated mountain existed, it may get eroded away. That question I can tell. But then why this much higher elevation volcanoes are formed is one thing is it lies with the geodesy and also the gravitational forces all has a role on it. That's how the researchers explain it.
So regarding this volcano, he is asking, there is no active volcanic activity at this time, so there will be no lightning.
Yes.
The second question, there are no active volcanoes. This volcanism stopped billions of years ago. It's not happening now. So.
Any other questions from the audience?
They're sleeping.
So I hope, yeah, if there are no other questions, I would like to propose a vote of thanks. So thank you, Dr. Archana, for accepting Science Forum's invitation for delivering this distinguished lecture on the topic, the geological proximity between Mars and Earth. And needless to say, this has been one of the very interesting topic or lecture delivered so far in ESF. As we all know that Mars itself is a very interesting planet and people are very curious to know more about Mars. And the title of the talk which you have delivered, the geological proximity itself has caught the attention of, I think it might have caught the attention of all the students and other researchers alike. So yeah, it's very exciting. Also, it's very exciting to see that your group is producing wonderful research literally out of the world results. So I wish you all the best for you and your group, and very happy to see you here in this forum. And I hope you will visit ENCESS for personal interaction with all the scientists here. And that also it's a standing invitation in that respect also from the side of ESF. So thank you, Dr. Archana, for your time in spite of your hectic schedule there, and also in spite of your sore throat problems, I understand. So thank you. Thank you for accepting our invitation and delivering the talk today. On behalf of the director and all those who have gathered in this forum, I extend my heartfelt thanks to you. So
thank you for giving this opportunity, and it's like coming back to the same place. I used to love those days. Okay, so thank you, and thank you, sir. Thank you for.
Thank you very much. Thank you.
Thank you.
We'll meet again sometime.
Yes, sir. Yeah, sure.
Thank you.